Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video here is to demonstrate how to handle frictional forces when you're talking about something like maybe a belt sliding across some sort of surface, or maybe a rope wrapped around a tree, and these sorts of situations. So we're looking at here, we've got this physical object here with maybe some sort of belt over it. And imagine two forces applied, a tension that I'm going to call T2 to the down and left, tension T1 lower right. And again, this thing, imagine, is rigid. It cannot rotate. So what's going to happen is we're going to talk about the frictional force maybe as this belt slides along here, or maybe an impending motion situation. So the million-dollar question here is, can we calculate the relationship between T2 and T1? Now, in this example, we're going to assume that T2 is bigger than T1. So the idea is that we're going to break this belt up into little pieces. So I'm imagining a little piece of arc length here where this interior angle I'm going to call ds. And I've already, in order to keep the video shorter, I've already drawn a free body of this little piece. Now, an important thing to realize. Right, here's the absolute center here. Here's a tangent line that touches right here. And that's going to be this pretty much exact spot in my free body. We have a normal force that's going to be acting up and right that I have drawn, and that normal would be infinitely small because we're talking about an infinitely small piece of this object. We're going to have a tension acting down and right, just slightly down and right, and then another tension acting slightly kind of down and left, again, from this horizontal line. That's because of this. You can even see this little tiny angular gap here in my picture. These angles, it's not too tough to show geometrically, would be d theta over 2 and d theta over 2. I called this value t. This tension here is going to be t plus some difference in tension. Right? This df here can be written coefficient of friction times the normal force. So I'm going to go ahead and write that at dn here. And all we're going to do here is we're just going to now take this free body and write a pair of equations. All right, first equation. The sum of all forces, I'm just going to say in the normal direction, is equal to 0, calling up and right the positive normal direction. We've got that force dn. The normal component of this is going to be opposite that d theta over 2, so we're going to have minus t sine d theta over 2 for this force vector. We're going to have another minus the normal component of this force vector, being careful. The hypotenuse is t plus dt sine d theta over 2. And I think that's it, because the frictional force here, this df, does not have a component in the normal direction, so equals 0. Next equation, I'm going to go ahead and write the sum of all forces. I'll just call this the tangential direction equals 0. So now I'm calling this the tangential direction. I'll go ahead and do down and right positive. We look at our free body here. We're going to have t times the cosine of d theta over 2 for this force vector, plus this force vector, which I'll go ahead and just write mu dn here, coefficient of friction times the normal, minus this guy's tangential component, again hypotenuse t plus dt, cosine d theta over 2 for the tangential component here of this force vector. And I think I have everything. This dn does not have a component in the tangential direction, so equals 0. So we've got a pair of equations to work with here, and now we're going to talk about a little bit about, how do we solve these things? Well, first, from trigonometry here, some things to consider. The sine of d theta over 2 is basically equal to d theta over 2. If you think back to calculus here, remember the limit of sine x over x is 1 as theta goes to 0, and d theta over 2, mathematically, that's a differential, basically 0. Not identically 0, but approaching 0. So this thing right here can be written t sine d theta over 2, and we've got another, looking at this equation, we've got another minus t sine d theta over 2. Those are just going to add to 0. Next product here, we've got this minus dt sine d theta over 2. And again, that sine of d theta over 2 can be written just d theta over 2 because of small angle approximation. All right, this product here, whoops, I feel like I missed something. dn, ooh, I gotta go back. Apologies in my video here. I'm gonna go back and evaluate that equation again. dn minus t sine d theta over 2 is minus t d theta over 2. This product here, these did not add to 0. They're both negative. So minus t sine of d theta over 2. And again, sine of d theta over 2 is approximately d theta over 2. So I'm just going to put minus t d theta over 2. And then the next is going to be this product here. Now, this thing right here, I'm going to write this off to the side, is dt times sine of d theta over 2. But sine of d theta over 2 can be written d theta over 2. And you notice this is the product of two differentials. So, you know, remember a differential is basically infinitely small. The product of two is infinitely smaller. So what I'm going to do is what's called a first order approximation here. I'm just going to say that this is basically 0. So then this equation, right, equals 0. These can now be just combined together. So we've got dn minus t d theta equals 0. So there's equation number 1, kind of simplified. Let's take a look at down here now. You notice we got these cosine of d theta over 2's. Well, cosine of d theta over 2, because remember d theta is a differential, so this is pretty darn close to just cosine of 0, which is 1. So I'm just going to write t plus mu dn minus t cosine d theta over 2. That's effectively going to be just minus t minus dt times cosine of d theta over 2. And again, remember the cosine of d theta over 2 is approximately 1. So I'm not even going to bother writing the 1, equals 0. So the tensions definitely will just add to 0. Mu dn minus dt equals 0. So there's our two equations now kind of cleaned up. 1, 2. Now the next move here is an algebra move. I'm going to go ahead and take equation 1 here and divide it by equation 2. So if we do that, whoops, actually to tell you the truth, I'm going to do a little bit more math here. I'm going to write this one dn equals t d theta. Take this one and write it mu dn, all right, coefficient friction times dn is equal to dt. All right, now I'm going to do the division. And let's see, how about we take this one, divide it by this one. The reason for the divisions is this will now go away. So we're going to have the coefficient of friction over 1, if we take this over this, equals dt over t d theta. This equation is fairly easily solved. The t might as well just stay there. The d theta might as well go on the left. So what we have here is coefficient of friction times d theta is equal to dt over t. And this is an equation here that can be integrated. This can be solved by direct integration. My limits on the right-hand side are going to be t1 to t2. Limits on the left-hand side are going to be from a theta 1 to theta 2. Now I'm going to go ahead and just call my theta 1 0. So in this picture, my theta 1 might be something like this, measured with respect to here, and I'm going to call that theta equals 0. And then my other bound on theta, or I'm sorry, on T2, is going to be this angle right here. So when we integrate this, basically what we get, I'm kind of running out of room. I guess I'll actually take this entire mess, just scale it down so we still can chat about it. All right, so integral mu d theta. Now mu is some constant presumably, so this is just going to be mu times theta. By the time we integrate d theta, we get theta, evaluated 0 to theta. So basically this is mu times theta equals, a little comment here, this is a variable of integration and this is a limit. Technically this should be something like integral mu d theta prime or something like that. It's not 100% kosher the way I have it written, but I'm going to keep going with the video. It's not super important for right now. This right hand side, let's see, integral dt over t, that's a natural log function. That's going to integrate to natural log of t2 over t1. This can be written as e to the mu times theta is equal to t2 over t1. So our tension T2 is going to equal our tension T1 e to the mu times theta. And this is pretty well demonstrated how to do this. Again, the way that you analyze friction acting along a belt or a rope or something like this, you pick an arbitrary little spot of it here, a little ds. This interior angle is then a d theta. You draw a free body of it, but some of these forces are differential forces. Like this normal, that's because we're looking at an infinitely small slice of it, and then our frictional force then becomes a differential frictional force. Our tensions are going to differ by an amount dt. Write a pair of force equations, use approximations like sine d theta is approximately d theta, or I'm sorry, in this example, sine d theta over 2 is approximately d theta over 2. And somewhere I use the fact that cosine of d theta over 2 is basically 1. And you get a fairly easily solvable first order differential equation relating T2 and T1. Hope this video helps demonstrate how to deal with friction for belts or ropes. Have a great day.